This is problem 14-99. One end of the 18-inch long bar AB shown in the figure is attached to a slider, which moves in a vertical slot. The other end is attached to a wheel that rolls on a horizontal surface. At the instant shown, the center of the wheel is moving to the right with a speed of 5 inches per second, and the speed is increasing at a rate of 2 inches per second squared. Determine the angular acceleration alpha sub a of the wheel and the acceleration a sub b of the slider b at this instant. Okay, so the new thing that they're asking us to find is now an angular acceleration. In the problems we've done in the previous sections, angular velocity was the furthest into the story that we were getting as far as the angular characteristics. Now they want us to take it a step further, and they want us to find angular acceleration as well, the acceleration of rotation. All right, so some of the things that they tell us is that B is only able to move vertical in the slot, right? So B moves vertical and A also only moves horizontal. All right. Well, but A is not only just the contact point here, but it's the whole wheel. So they're not asking us to find the angular acceleration of AB. That would be alpha AB. They're asking us to find just alpha A. So that's the cylinder, which is why the cylinder has been brought into the problem. Okay, so let's see if we can figure out relationships between information that we know and the information that they want us to find. All right, first let's talk about the things that they've given us. There's a lot of information here that's been given to us, so let's make sure that we keep track of everything. First, let's go ahead and draw the bar AB. Let's keep track of the fact that this is 30 degrees. This is point B. There is an 18-inch long rod. There is also a disc with a diameter of 4 inches. Okay, and it can only move. I'm going to go ahead and draw. There's a direction of B and a direction of A. And let me make sure I label A. So A is the actual disc. All right. Some other things they give us are that at the instant shown, the center of the wheel is moving to the right with a speed of 5 inches per second. Okay, the center of the wheel. So that means that we could say that the velocity as a vector of A, and they said it is 5 inches per second. So 5 I hat. We can just go ahead and do the I hat, J hat vector situation now. It's plus 5 because the wheel is moving to the right, and that's the positive direction. Okay, and then they say the speed is increasing at 2 inches per second squared. So that means that the acceleration of A, now the linear acceleration, okay, is increasing at a rate of 2 inches per second squared. So increasing, so positive to the right, and also only I hat. All right, so that kind of helps us keep track of not only what kind of information, this is a V or an A or an omega or an alpha, so what kind of information, and also the actual vector directions. So we don't have to think about that particular aspect of it anymore. Okay, and then let's keep track of what they want us to find. So they want us to find alpha of A, and then they also want us to find the linear acceleration of B. All right. Now, we need to take the information we have, whether it's distances. Now, by the way, distances or angles, things like that. The angular position of rod AB right now is 30 degrees. I just really want to point that out, that there is an angular velocity omega that we've been dealing with. There are now we're being asked to talk about angular accelerations. Okay, don't forget that this is an angular position. So there are 3 linear characteristics and 3 angular characteristics of all of the rigid body objects. So now we've got a rigid body rod and we have a rigid body cylinder. All right. Now, what can we do with this information? Well, let's go ahead and get started with, I'm just going to kind of throw this out there and you can see how this works. Let's talk about the velocity of A as a vector being equal to the velocity of C as a vector plus the velocity of A relative to C. C, well, where is this C? Well, when you think of A as a disk and A having some sort of radial length, then A's rotation, so I'm going to redraw A here. So this is A. A's rotation is rotating around a center point. Like let's say we have a bunch of spokes. So since the wheel is rolling, something that is talked about on page 131, and please go back now and look at page 131 so that way you can see what is so important about that particular page. I didn't talk about it in the past. I wanted to wait until it became relevant and useful. The instantaneous center of zero velocity, if you look at page 131 in the book, talking about a rolling wheel, is always at the point of contact of the wheel with the ground. Now, there are some other concepts to think about that aren't as necessary to consider right now, but will be in the future. That if a wheel is rolling, the tires on your car as you're going down the highway, as the wheels are rolling, the contact point at the bottom of your wheel is not sliding against the ground. If you slam on the brakes and the car skids to a stop, then that is the wheel sliding along the ground. But when a wheel is rolling, the wheel is not sliding. And since the wheel is not sliding relative to the ground and the ground is not moving, that means that the point of the tire at contact with the ground is not moving during that instantaneous moment. So as the wheel rolls forward and reaches a new spot, so let's say, let me try to illustrate this a little bit better with the idea that maybe there is a location on the wheel that is pointed straight down, like a marking on the wheel. And as the wheel rolls forward, now maybe the marking has rolled around to in this direction to this new position. The contact point with the road is still down here, but that is the new instantaneous point of zero velocity. Okay, so the old point has rolled up to this position and is now being flung around over the top of the wheel. But down here, this point is now not moving. Okay, so that is what point C is in my equation. So point C is down here at the bottom of the wheel, which now means it's an instantaneous center of zero velocity and is 0. Okay, so now do we know the velocity of A? Yes, we were told that the velocity of A is 5I. All right, so that means 5I hat equal to 0 plus the velocity of A relative to C. Well, what is the velocity of A relative to C? It's going to be well, it's 5, but we're going to write it in different terms. We're going to write it in the lever arm times omega A, because the whole disk is A. All right, so that means that it will be 4 times omega A. All right, now we don't necessarily need this I hat, so let me just get rid of that to keep things a little more simple. Okay, so now that means that omega A is equal to 1.25 radians per second and in the clockwise direction. All right, we learned something new. We got an omega A. All right, now what is that going to do for us? Well, that is where the new information about finding accelerations comes in. So we've had a relative velocity diagram that we have been using to create these equations where you have one point velocity, another point's velocity, and the first point's velocity relative to the other point. All right, now we're going to have a relative acceleration equation and a relative acceleration diagram. And there are some new terms involved in that. All right, first is the equation. So the acceleration of A equal to the acceleration of C plus the acceleration of A relative to C. All right, so what do we know and how do we find information we don't know? Well, first is to talk about that if we have the disk and if A is where the wheel is connected and C is the point of contact with the ground, I'll redraw the diagram here. So here is A and C. which is just where I have on the wheel. So actually, let me use some colors here to make things a little more clear. So if I change my diagram to have a blue, so this line here going from A to the point of contact is going to be what I am drawing there. All right. And so now we have our acceleration of A. Well, that's going to be what we were given in the problem. Acceleration A is 2I. All right, so I'm going to also do some colors here. So 2I hat is the acceleration of A. All right, the acceleration of C. Well, we know that C is not moving right now and is about to leave the ground. So this takes a little bit of either it makes sense to you or you kind of got to press the I believe button on this. I haven't really found a way to explain this in any other way other than imagine that the point on the wheel that is in contact with the ground now will get whipped around to the top of the wheel. All right, but in order to start getting whipped around the wheel, it first has to leave the ground. So at this instantaneous moment, point C, the part of the wheel that's in contact with the ground, has to go straight up. Just during this instantaneous moment that it's on the ground, it has to go straight up to leave the ground. All right, so that's either going to make sense to you or you're just going to have to remember that this is true and press I believe on this. Okay, so that means that we don't know the magnitude. However, we do know that it has a direction of j hat. All right, now here comes the new tricky part. Using this relative acceleration diagram to fill out the last term of the relative acceleration equation. All right, so let's pick a color. Let's go with this kind of purple color here and fill in this diagram. So accelerations, relative accelerations are going to have two vectors. There's going to be a tangential vector and there's going to be a normal vector. Okay, remember, this is not velocity, this is acceleration. This is how the point is going to be moving relative to another point. All right, let me move this a little bit to get it away from the other diagram. All right, and I'm color coding things to help you with the terms. Okay, so the purple arrow is going to have a value of the radius times the angular acceleration. And the green arrow is going to have the values of the radius times the angular velocity squared. All right. Now the derivations and how this is explained is in the chapter, so go take a look at that. But this is what the terms are. And in this case, the lever arm is going to be 4, and it's going to be the omega c value. Okay. What is the omega c value? Well, it's actually still technically the same as omega a. All right. So we do know that omega a is 1.25, but this is a squared term. Now, the lever arm for the tangential acceleration term is going to be 4, and then it's going to be times alpha, but it's going to be alpha c, right? And those are the two terms that we are going to be using in the equation. So we know that the tangential acceleration is going to be 4 alpha c I hat. And then we know that the normal acceleration is going to be plus 4 times 1.25 squared j hat. All right, so I've tried to color code everything, help keep things kind of straight. And the different vectors, these are linear accelerations that are being created by angular accelerations and angular motions. All right, and so now we have unknowns, two unknowns, but we have I hat and j hat equations. So we have two equations, two unknowns. And now we can solve for these values. All right. What do we care about though is we care about the angular acceleration of c. Okay, so I'm going to go ahead and solve for that value. The angular acceleration of c, sorry, which is alpha c, not the AC. Alpha c is 0.5 radians per second squared and in the clockwise direction. Okay, now what? Well, the question is asking us to find alpha a and the linear acceleration of b. All right, so we need to learn something about b in order to find out what's going on with the acceleration of b. Oh, I forgot to mention though that actually we have found the answer. By finding the angular acceleration of c, that basically we found the angular acceleration of a. So I'm really actually being a little misleading by calling this the angular acceleration of c. Right? This is the angular acceleration of disk A. Right? So sorry if that might be confusing you, but we have found the answer to the first part. This is the angular acceleration of A. All right, now to find the linear acceleration of B, we need to learn some things about bar AB so that way we can figure out what slider B is doing. All right, in order to do that, I think we're going to have to make a new page and let's go to the relative velocity equation. So the velocity of B is equal to the velocity of A plus the velocity of B relative to A. All right. Well, what do we know? Do we know anything about the velocity of B? No. So let's go ahead. Well, that's not true. We don't know nothing about velocity B. We just don't know the magnitude of velocity B. We know that velocity B can only move in the vertical direction because it's restricted in the slider. So we will only have a j hat term for velocity B. Do we know anything about velocity A? Yes, we were told in the beginning that the velocity of A is equal to 5. So I should actually be writing 5I hat because A can only move in the horizontal. All right, now velocity of B relative to A. Hopefully it's not a surprise already that we're going to have to do one of those relative velocity diagrams. Okay, so we have point A, and then we have point B, and then we'll have the motion of the velocity of B relative to A. All right, and so in order to get the terms, we need to know the angle. So they give us that the angle was 30 degrees. They had 30 degrees coming off of B, but also it's the same on the other side coming off of A, right? And so we know that the lever arm is 18 inches. So that'll be the R. And then the omega AB is something that we don't know. So if we do that, the velocity of B relative to A is 18 omega AB, and then times the negative cosine of 30 degrees I hat, and then plus sine 30 degrees J hat. There we go. All right, now we can find the omega AB and the velocity B. Two equations, two unknowns. Sorry, that got a little messy there. But remember, the J hats and the J hats, and then the I hats and the I hats are in their separate equations. All right, just to make things a little more clear. So the I hats, the X direction, I'll go ahead and write this one out just in case people have been struggling. So 0, 5 minus, 18 omega AB cosine 30 degrees. And then the y terms are the velocity of B, which is unknown, equal to 18 omega AB sine 30. All right. So the answers are omega AB is equal to 0.321 radians per second in the counterclockwise direction, and the velocity of b is equal to 2.89 inches per second going upward. Okay, what did that do for us though? Because really, in the end, we're trying to find the acceleration of b. Now, point b. So that means that it's going to be a vertical acceleration only is possible. But the value is found indirectly due to the fact that they give us at the beginning of the problem an acceleration for point A. They told us that point A is accelerating at 2 inches per second squared in the I hat direction. All right, so if we do the relative acceleration equation, so the acceleration of B equal to the acceleration of A plus the acceleration of B relative to A. All right, what do we know about the acceleration of B? Well, we know that B's acceleration can only go up. So the acceleration of B's magnitude in the j hat direction is equal to the given acceleration of A of 2 inches per second squared in the I hat direction. And then we have to figure out what this the acceleration of B relative to A is. Well, that means we need to do the relative acceleration diagram. All right, so if we have A and we have B, then don't forget that we are going to have a tangential acceleration and a normal acceleration. All right, now the lever arm is 18, and the 18 will be the lever arm times the angular velocity of AB squared, and the tangential will be the lever arm of 18 times the angular acceleration of AB. These are just the formulas. It's going to be the same every single time. Okay, you just got to remember which is which. All right, we do know that we have a 30-degree angle. So that means that the equation is going to be those two terms added together. So what do we write? We go 18 and then alpha AB. So this is the tangential term, but the tangential term is at an angle. So that means we'll have an I hat and j hat just for this one term. That is one of the two vectors that are going to be added up. All right, so remember, we're just doing the tangential right now, and there's going to be a negative cosine 30 degrees I hat plus a sine 30 degrees j hat. All right, that's just this arrow. All right, next, in fact, I'm just going to go ahead and to help minimize confusion, I'm going to go ahead and change the color of this arrow so that way we can keep track. This purple arrow is now the 18 omega AB squared. All right, that's going to be the next term. So that'll be 18, and then we already know omega. We found omega AB here. So it's going to be 0.321 squared. All right, and then the I hat j hat. So negative sine 30 degrees I hat minus cosine 30 degrees j hat. All right, so the red math is for the red arrow, the tangential acceleration, linear tangential acceleration. By the way, just to make sure I haven't written this in a while, it's this acceleration. It's linear, it's A, not alpha. And then purple is going to be the normal acceleration, linear, A, not alpha. All right, this is two equations, two unknowns here. So the answer to this is alpha AB is equal to 0.0689 radians per second squared, okay? And just alpha B, or sorry, AB, the acceleration, linear acceleration of B is negative 0.984 inches per second squared. This is in the downward direction.